Thanks for clicking on my presentation. My name is Mathias Gotsmy, and I want to present my poster with the title Identification of Linked Metabolites Allows a Reliable and Quantitative Analysis of the Finger Sweat Metabolome. So why is the metabolome of sweat interesting? Well, you can find quite a lot of compounds in there, not only water and ions, but also amino acids, lipids, organic compounds, vitamins, and so on. So it's a really nice source of biomarkers, and it can be sampled relatively easily, a lot easier than, for example, blood. So my experimental partners already designed a very nice sampling methodology where you just wash your hands and then you press your index finger and thumb on a filter paper for 1 minute, and with that it is already enough to extract metabolites and to measure them with LC-MS. So as a proof of principle study, they measured the concentration time series of caffeine after a single dose ingestion of caffeine. And on the left, you can see the concentration time series of caffeine in its major degradation products, paraxanthine, theobromine, and theophylline. And what you can see is that the curves look roughly okay. They start at low concentration and then they go up and then they go down again. However, there seem to be big errors. And these errors are actually due to the sweat volume, which is something which can change. So for one sample time point, we sweat more than for another one, but we can't measure it because the volumes are too small. So the question for me was, how can we find a normalization strategy that accounts for this sweat volume? And what I found out is that we can actually try to link metabolites. So when you just write down one metabolite, you actually always measure M, which is the mass that consists of the true concentration of a metabolite C in the sweat times the sweat volume. But if you look at two metabolites, for example, caffeine and paraxanthine, and take the ratio, so M caffeine over M paraxanthine, then it actually equals to the concentration of caffeine, the true concentration of caffeine over the true concentration of paraxanthine, because the sweat volume cancels out because it's the same for both metabolites at one time point. And this is actually clearly visible in this plot here, where again, you have this quite nasty looking caffeine time, raw time concentration of caffeine and paraxanthine, but as soon as you divide them, you get a really smooth line, a black line. So with that and with some pharmacological modeling, we can actually build an equation system where we not only fit kinetic constants for the degradation of caffeine, but we also fit sweat volumes at every time point. And including also initial dose of ingestion and bioavailability and the volume of distribution, we can get actually absolute concentration values for our compounds. So the question is, of course, how robust or how well does this work? We measured 41 time series after the ingestion of caffeine. And as I said, we also estimated kinetic parameters from our model. And here we actually see a PCA of the kinetic parameters, and time series that were sampled from the same human have the same marker shape. So for example, you can see there are 3 squares and they cluster quite close together. And the same is true with the diamonds and with the triangles and the stars. So with that plot, we can really show that our model is robust enough that if you sample the same person 3 times, you get similar values, but it's flexible enough that you can really see difference between different people. So There are also some normalization strategies from literature. However, they are not really optimized for sweat, and that's something you can see in this plot. So here we just show the RMSE of the fit of a kinetic model without any accounting for sweat volume to our concentration data. And actually, for example, normalizing with creatinine or amino acids or the total signal does not work at all for sweat. And with our model, however, which is shown in red, we get quite low RMSE. And we also built, with some training data from our model, a random forest prediction model. And this predicts the sweat volume, and this still has a lot better RMSE than other methods. So with that, I conclude my presentation. I wanna acknowledge my partners, especially the Gerner Group and Julia Brunmeier, who was in charge of the experimental part of this work, and Jürgen Zangellini and the Zangellini Group for helping me with the mathematical modeling. And finally, thank you for watching my presentation.